models of the atom. Some of these we've already went over, but some of them are going to be new to you. J.J. Thomson came up with one of the first models for the atom, and we talked about this before, but J.J. Thomson's model looked like this. Electrons were stuck in place. Called it the plum pudding model, but the electrons didn't move. They were stuck in place, kind of like a chocolate chip cookie. No protons and no neutrons, just electrons in his model. The next guy that developed a model, Ernest Rutherford, did the gold foil experiment. And from the gold foil experiment, he determined that that atoms had a nucleus, and in that nucleus you had your protons and your neutrons. That was where most of the mass was, and I've drawn the nucleus way too big here, but the nucleus is very, very, very small. Electrons are outside the nucleus, like this. But his model could not explain the chemical properties of elements. And so the next guy comes along, Niels Bohr, and produces his model for the atom. Bohr said that electrons are found only in specific circular paths around the nucleus. So the nucleus is the common part here for all atoms now. We have a nucleus. Now we're looking at electron movement. In the Bohr model, these were called orbits. And electrons orbited the nucleus, much like planets orbit the sun. Each orbit has a fixed energy, which is called an energy level. And electrons can jump from one energy level to another by absorbing a certain quantum of energy, which is just an amount of energy. Higher energy would be further from the nucleus. And the amount of energy gained or lost is not always the same. So in the Bohr model, we have the nucleus, protons and neutrons, which is, again, very, very small. Outside the nucleus, you have electrons that circle the nucleus in these orbits. And electrons can jump from one energy level to another. So an electron here could jump up to this energy level as it absorbs energy. And then if that electron wants to come back down, it can release energy and drop back down to a lower level. So electrons can jump those energy levels. But the main idea with the Bohr model is electrons circle the nucleus. Now, this is probably the model that you've been taught, but this is an incorrect model for the atom. Yes, it's easy to understand. Electrons circle the nucleus, and it's very easy to understand with the concepts that we teach. However, this is an incorrect model for the atom. The Bohr model is not correct. The correct model for the atom, the one that we use today, is the quantum mechanical model. And this is a very complex model. It's very difficult to understand at first. But the quantum mechanical model does not involve an exact path of an electron around the nucleus. The fact of the matter is we don't know where electrons are inside an atom. So the quantum mechanical model describes how likely it is to find an electron in various locations around the nucleus. It's based on probability. Based on probability, 90% of the time an electron is found within the electron cloud. So, quantum mechanical model is all based on the fact that we do not know where an electron is at any given moment in time, and so we know that electrons are going to move randomly, and that is what this model is based on. So we're going to go through some concepts here with the quantum mechanical model, and it is very difficult to understand at first, but just know this: electrons move randomly. So if you get nothing else out of this, electrons move randomly. They do not circle the nucleus. Okay, in the quantum mechanical model, the correct model, electrons can have different energy levels. And we're going to denote the energy level by a quantum number. Now, there are 4 quantum numbers that completely describe where an electron is. The first quantum number is N. N tells us the energy level. N can be anywhere from 1 up to 7. If you go back to the periodic table, you notice that there are 7 rows on the periodic table, and these correspond to the principal quantum number N. So N tells us the energy level. Each energy level contains a sublevel or a subshell. The number of subshells in any main energy level is equal to the number of that main energy level. So for example, how many sublevels or subshells are in main energy level 2? Well, if n equals 2, I have 2 subshells. How many subshells are in main energy level 4? N is 4. Well, if n is 4, that means I have 4 subshells, 4 sublevels. So what are the sublevels? The sublevels are S, P, D, or F. And I will show you what these look like in class. But S sublevels are spherical. That's the region of space where you're likely to find an electron. P are dumbbell-shaped. D are cloverleaf. And F are complicated. So these are the 4 sublevels or 4 subshells. These are the 4 subshells. Each subshell is designated with the quantum number L. That's an L. So N tells us the energy level. L tells us the subshell. L can be anywhere from 0 up to 3, depending on if you're an S, P, D, or an F subshell. So we're only going to define 4 subshells, but in reality, there's a much larger number of subshells. Atomic orbital. Region of space in which there is a high probability of finding an electron. Each subshell, the S, P, D, and F, consists of a certain number of atomic orbitals. An atomic orbital is another name for an electron cloud. So electron cloud, atomic orbital, same meaning. So here are the 4 subshells, S, P, D, and F. Within those subshells, you have orbitals. S only has 1 orbital, P has 3, D has 5, and F has 7. And that's always the case. So it goes 1, 3, 5, 7. And those orbitals are numbered. This is the 3rd quantum number. So we had quantum number N, energy level, quantum number L, sublevel, and then the 3rd quantum number is M. M tells us what the orbital number is. So M tells us the orbital number where the electron is likely to be. Okay, atomic orbitals. N equals 1 has 1 subshell. N equals 2 has 2 subshells. N equals 3 has 3. You see the pattern. N equals 1 has 1 orbital total, and that is an S orbital. N equals 2, if you add up the number of orbitals in N equals 2, you have a 2s and a 2p, but if you add up the total number of orbitals, you have 4 orbitals in N equals 2. N equals 3, if you add these up, I've got 1, 3, 5, you add those up, you get 9 orbitals. And then when you get to N equals 4, add these numbers up, and you get a total of 16 orbitals. So you should kind of see a pattern here. N equals 1 has 1, N equals 2 has 4, N equals 3 has 9, and N equals 4 has 16 orbitals. So the pattern tells us that the number of orbitals within the main energy level is N squared. So if I'm in energy level 7, and I want to know how many orbitals, how many regions of space am I likely to find an electron, it's simply 7 squared. So there would be 49 orbitals in that 7th energy level. Okay, so the orbital where you're likely to find an electron, no more than 2 electrons can occupy an orbital. And electrons act as if they are spinning, gives us the 4th quantum number, S. S can be positive 1/2 or negative 1/2, depending on the spin of the electron. So you have 4 quantum numbers that completely describe where an electron is likely to be within an atom. NLMS. The maximum number of electrons within a main energy shell is 2n squared. So if I want to determine how many electrons can possibly occupy energy level 7, I would do 2 times 7 squared. 49 times 2. So an energy level 7 can hold 98 electrons. Now, the quantum mechanical model is based on probability. It is difficult to understand, and I've kind of went through the basic concepts here. We'll get more into this in the next section, but don't worry if you don't completely understand this model, because it is very complicated to learn at first, and we will delve more into this in class.